So thanks to the organizers for inviting me to speak here. I'm really happy to be here. I'm going to be talking about space-time reflection anomalies in 2+1D topological quantum field theories. So the overall goal of this research program is to understand 2+1D topological quantum field theories where you have a global symmetry. And we want to understand the interplay of the TQFT with that global symmetry. Now, my background is in condensed matter physics, and the motivation from condensed matter physics for studying this problem is that we want to have a theory of all the possible phases of matter, all the possible quantum phases of matter, and the simplest types of quantum phases of matter are what we call gapped phases of matter. Gapped phases of matter have the property that correlation functions of operators are short-ranged, and so in a sense they're kind of the simplest phases of matter. So for that reason, that's the kind of phase of matter that it's most natural to study and completely understand first. In condensed matter physics, these phases of matter go by the name of symmetry-enriched topological phases of matter. They're called SET states. And some famous examples of these are fractional quantum Hall states, which were discovered first experimentally in the early 1980s, and also quantum spin liquids, for which there's an ongoing experimental search. And the theory is in continual development since the late 80s. So the work that I'm going to be presenting is based on a series of papers that I've written with a number of collaborators over the years. Meng Cheng is an assistant professor also in condensed matter physics at Yale. Parsa Bonderson is at Microsoft Station Q. Kevin Walker and Jianhong Wang are mathematicians at Microsoft Station Q. And Xiaoming Zhang is a postdoc at Microsoft Station Q and KITP. Okay, so let's start with just discussing 2+1D TQFT by itself and what's already been known for a long time. 2+1D TQFT is characterized by two things. One is a mathematical object known as a unitary modular tensor category, C. And the meaning of this is that it describes the braiding and fusion properties of topologically non-trivial quasiparticles that exist in the phase of matter. These topologically non-trivial quasiparticles are described in the modular tensor category in terms of the isomorphism classes of simple objects of the category. Now, this unitary modular tensor category almost completely captures the properties of the TQFT. There's only one additional piece of data that we need to specify, and that's the chiral central charge, which is denoted by lowercase c. Now, modulo 8, the chiral central charge is already determined by the unitary modular tensor category, so the only extra thing to specify is the remainder mod 8. So let me give you a brief review of the unitary modular tensor category. Here we have the isomorphism classes of simple objects. We have a finite list of them. These are what we call the particles or quasiparticles. These particles have fusion rules. We have these fusion coefficients. What this means is that given A, B, and C, we have a vector space V, A, B, C. The dimension of this vector space are these fusion coefficients N, A, B, C. And we have a dual space, the splitting spaces, denoted here. And the two important pieces of the modular tensor category are these F symbols, which are maps from this vector space ABCD to ABCD, but decomposed through a different channel. These are the F symbols, and then we have braiding, which are captured by the R symbols. So this diagram is related to this diagram by the R matrix. There's a set of consistency conditions, the famous pentagon and hexagon equations. If you solve the pentagon equation, then what you have is a fusion category. If you solve the hexagon equation, then what you have is a braided fusion category. There's an important class of transformations, which maybe if you're a mathematician, you don't really think about this very much, but as physicists, where we want to do everything very concretely, we think about a lot is there's a set of gauge transformations, which are just basis transformations in these vector spaces. And these cause the F symbols to change by these gauge transformations in schematically the following way. So this data, the fusion coefficients, the F symbols, and the R symbols, in mathematical parlance, this This provides what is called a skeletonization of the unitary modular tensor category. It basically just boils down the whole mathematical structure into some list of concrete numbers that we can compute with. The gauge invariant quantities, the quantities that were invariant under these transformations, correspond to physical topological invariants that, as condensed matter physicists, we can measure in numerical experiments or real experiments. Some examples are this topological twist, which relates this diagram to this diagram by a phase, the topological twist. There's the modular S matrix. The fact that the tensor category is modular is the requirement that this matrix be unitary. And finally, we have the quantum dimension, which is the value assigned to this diagram. Okay, so now we want to consider 2 plus 1D topological quantum field theories with the global symmetry group G. Now, I'm going to give you first a review of kind of the general theory, and then I'll focus on space-time reflection symmetries. Now, independently of any global symmetry, the modular tensor category already has its own group of intrinsic symmetries, completely independent of any global symmetries. This is referred to as the automorphism group, or AUT of C. And the way that you think about AUT C is as follows. You think of maps from the category into itself. These maps can permute the particles to a different type of particle, but they have to have the property where they keep the fusion rules invariant. Similarly, the quantum dimensions are invariant. And they map these fusion and splitting spaces to the permuted ones, but there could be this basis transformation involved as well. Now, if phi is space-time parity preserving, then the twists and the S matrix are also invariant under this transformation, and the R and F symbols are also invariant after permuting the labels up to a gauge transformation. However, if phi is space-time parity reversing, we get complex conjugates in the twists and in the F and R symbols. Now, in addition, we have what we call natural isomorphisms. Those keep the particles invariant, and the way that they act on the fusion spaces is by this very simple trivial decomposition. So in a sense, these natural isomorphisms are like do-nothing transformations, but we need to keep track of them, because these maps phi don't by themselves form a group. It's equivalence classes of phi up to these natural isomorphisms, which form this group, which we refer to as AUT C. So this is, again, it's the group of intrinsic symmetries of the TQFT. From the point of view of condensed matter physics, we think of these as emergent symmetries. It doesn't matter at all what the global symmetry of the problem is. You can break this global symmetry to whatever you want in the ultraviolet, but no matter what you do, as long as your system is described by this TQFT, you have these emergent symmetries coming out. Now, one thing that's useful to note is that in the case where these transformations are space-time parity preserving, in the mathematical literature, this AUT C is known as braided autoequivalences. But if you allow the maps to be space-time parity reversing, then I don't think that the equivalent kinds of maps have really been studied in the mathematical literature, so correspondingly I don't know what they would be called. Okay, so now we're going to add a global symmetry group, which is capital G. The first thing that needs to be specified is a group homomorphism, rho, from G into AUT C. So the way that you can think about it is, suppose that you have a set of, in your space, you have 3 particles, A, B, C, and you apply your symmetry transformation. Well, those A, B, C could be permuted to different particle types. And there's an action on this vector space, VABC goes to the permuted one, and if we use explicit basis states, there's in general this possible basis transformation as well that could come along with it. So this rho G also acts on the R and F symbols, and they give you back the R and F symbols up to these basis transformations. And these properties guarantee that any diagram that you write down, any closed diagram of particles, is G-symmetric. Now, one thing to note is if G is space-time parity reversing, actually there's also extra complex conjugates that come into play here. Now, when we look at rho G composed with rho H is not necessarily rho GH. Remember, we have to mod out by these natural isomorphisms. Now, in general, this natural isomorphism kappa does not have to be 1. And when kappa is not 1, then you get an interesting feature that arises. This rho defines an element O, which lives in the third cohomology group of G, with coefficients in a abelian group A, which I'll define in a second. And we have this action rho, where G acts on A through this rho that we've defined. Now, what is A? A is the group of particles in the modular tensor category which are abelian, meaning that they have quantum dimension 1. So these are the abelian anyons of the theory. They form a abelian group under fusion. Now, in terms of more modern language, you can think of this A as the one-form symmetry group of the TQFT. Now, in general, if you want to compute this O, you need full knowledge of the F and R symbols. So it's a rather tedious task to do this. Now, what is the meaning of this O? It turns out O is an obstruction to what we call symmetry localization, which I'm going to define in a slide. So, in other words, this O, if O is non-trivial, that means that you have an obstruction to the theory possessing the global symmetry group G together with this action of rho. Okay, now to go further, and for me to be able to define symmetry localization and then what happens when the obstruction vanishes, we need to consider combining this 2 plus 1D TQFT with additional local degrees of freedom. If you don't have any global symmetry, then you can always ignore these local degrees of freedom. And in fact, the whole point of TQFT is to sort of strip off all the local degrees of freedom, leaving behind only the non-local ones. But if you have a global symmetry, you actually do need to take into account the possibility of extra local degrees of freedom. And so in the presence of G, these local degrees of freedom can have a non-trivial interplay with the topological quantum field theory, and they cannot be ignored. So as a case in point, recall in general, we had rho G composed with rho H, gives us rho GH, but up to this natural isomorphism, and so this kappa need not be 1. And if you were trying to make your TQFT G-symmetric, this should worry you, because it means that your states don't form a faithful representation of the symmetry group. So you need to sort of remedy the existence of this kappa by adding some extra local degrees of freedom. Okay, so now imagine we've added some extra local degrees of freedom and we have our global state of the system. The vacuum state is G-symmetric, so R is the representation, the unitary representation of the symmetry group element G. The ground state is symmetric, so we have RG on the ground state, it gives us the ground state back. Now we can consider a state with 2 particles. This is space, and I have 2 particles, A and its conjugate A bar over here. And we can ask, what happens when we apply this symmetry group element, RG? The idea of symmetry localization is the idea that the way that RG acts on the state is that it permutes the particles. So A goes to GA, A bar goes to GA bar. And correspondingly, we get this UG transformation that came from rho that I defined a few slides ago. But because we have additional local degrees of freedom now in the problem, we also have additional unitary transformations, U1 and U2, which act in the neighborhood of these 2 particles, as I've shown over here. So this approximation that the symmetry action on the state decomposes in this way is the assumption of symmetry localization. Okay, it's basically the intuitive idea that the ground state is G-symmetric, so when you apply your symmetry transformation, nothing really happens anywhere except for the locations near the particles up to some overall non-local transformations due to the TQFT state space, which is captured here. So this assumption is only consistent if this obstruction, which lives in H3, is trivial. So you can look at the specific details of that in this paper. Now, if this obstruction vanishes, then we can go further and we can define a notion that we refer to as symmetry fractionalization. This is the idea that the particles can carry fractional quantum numbers of the symmetry group. So a cartoon way of understanding this, which is not actually correct in complete generality, but is often useful, is that you can think of the particles as themselves as carrying projective representations of the symmetry group. So even though the global state of the system may form a linear representation of the symmetry group, the particles themselves can form a projective representation. So a nice example to think about, which will be useful later as well, is imagine that you have time reversal symmetry, where time reversal squares to 1 in all physical states. However, on each particle, you can have the situation where locally time reversal squares to -1. That's the situation where you have a projective representation of anti-unitary time reversal transformation. And it means that locally, the particles could carry along with themselves a local two-dimensional space of states, which transforms non-trivially under time reversal. Okay, now when we think about symmetry fractionalization, the general result that comes out is that symmetry fractionalization can be classified by the second cohomology group of G with coefficients in A. Again, we have this twist by rho, where G acts on A through rho. Now, importantly, this classification is such that symmetry fractionalization forms a torsor under the second cohomology group. That means that the second cohomology group itself doesn't characterize symmetry fractionalization. What it means is that different symmetry fractionalization classes are related to each other by elements of this second cohomology group. So let me step back and summarize what's happened so far. 2 plus 1D topological quantum field theories with a global symmetry group G. So far, we've found that they're partially classified by the following data. We have to specify this group homomorphism from G into odd C. That tells us how the symmetries permute the particles. Now, if this obstruction, which lives in H3, is non-trivial, then we have this symmetry localization obstruction, and even the notion of symmetry fractionalization is not well defined anymore. But if this obstruction vanishes, then we can define symmetry fractionalization, and the different symmetry fractionalization classes are related to each other by elements of H2 over here. Now, characterizing the symmetry fractionalization class itself requires additional data that I haven't told you about yet. But let's proceed. So if this obstruction is trivial, and we can pick a symmetry fractionalization class, now this symmetry fractionalization class can be anomalous. So that's what we might call a symmetry fractionalization anomaly. In the language of high energy physics, it would be called a 't Hooft anomaly. So a nice example of this was provided by Senthil and Vishwanath in 2013. I think it was the first example in the context of topological quantum field theory, where the example was, imagine you have Z2 gauge theory, and the electric particle and the magnetic particle, both of them locally carry t squared equals -1, but globally you have time reversal symmetry with t squared equals +1. It turns out that this assignment of fractionalization of symmetry quantum numbers to the particles has a 't Hooft anomaly associated with it. Now, if our symmetry group is unitary and space-time parity preserving, we know how to classify these anomalies. These 't Hooft anomalies are classified by the fourth cohomology group of G with coefficients in U1. And physically, what this means is that the 2 plus 1D theory must exist at the surface of a 3 plus 1 dimensional topological quantum field theory. But importantly, that 3 plus 1D TQFT is invertible. And H4 of GU1 is precisely what classifies G-symmetric invertible TQFTs in 3 plus 1 dimensions. Okay? Now, you might ask, well, okay, this is the classification. Exactly how would you compute the 't Hooft anomaly? Now, if G contains only unitary space-time parity preserving symmetries, then what we can do is we can insert symmetry defects associated with the symmetry group capital G, and then we can ask about grading and fusion properties of the symmetry defects. And that takes us to a new algebraic structure, which is called the G-cross graded tensor category. So these G-cross graded tensor categories ultimately are classify or characterize TQFTs with G symmetry, at least when G is unitary and preserves the parity of space and time. Now, this G-cross graded tensor category provides explicit formulae and consistency conditions, consistency conditions that are analogous to the pentagon and hexagon equations, but generalized to the G defects. And solving these consistency conditions can allow you to compute all the Tohoku anomalies and completely characterize this 2 plus 1D TQFT. But again, where the symmetry G is unitary and space-time parity preserved. So now this raises the question, how do you understand situations where you have space-time reflection symmetries? So that's the subject of the rest of my talk. I'm going to focus on space-time reflection symmetries. And I want to discuss three things. I want to discuss how you characterize symmetry fractionalization when you have space-time reflection symmetry. I want to discuss Tohoku anomalies, how you compute them, and then finally I want to develop some understanding of this H3 obstruction that appears in the context of space-time reflection symmetries. Okay, so first off, characterizing symmetry fractionalization. So suppose that we have time reversal, T, and again, T squares to 1 on all global states. So we refer to this as Z2T. Okay, just the group Z2, but we put a superscript T to remind ourselves that this is time reversal, so it needs to be treated somewhat differently. So if the particles are invariant under the action of time reversal, then we can define a quantity which we call A to A T, which is plus or minus 1. And A to A T is basically capturing what the local T squared value of the particle is. And again, as I mentioned earlier, if T squared equals minus 1 locally on a particle, what that means is that that particle carries a projective representation of time reversal symmetry, and therefore it carries along with it a local two-dimensional vector space. Now, this A to A T needs to satisfy a number of consistency conditions. I won't put the full general ones here, but for example, the consistency conditions I need to satisfy are if A and B fuse to C, then A to A times A to B should be equal to A to C. And another important one, which will come up in the rest of my talk, so please remember it, is A to C is equal to the topological twist of C whenever C itself is invariant under time reversal, and furthermore, when C is the outcome of fusion of another particle, A, and its time reverse counterpart. So if I take A, its time reverse counterpart, fuse them together, and C comes out, then you can show that the T squared value for C must be equal to its topological twist. So in particular, this means C needs to be either a boson or a fermion. Now, for spatial reflection symmetry, the story is similar, although it's also somewhat different. Suppose that we have spatial reflection symmetry, R, where R squares to 1. We're going to refer to this as Z2R symmetry. Now here, what we can imagine is the following. Suppose that you have the 2 plus 1D system defined where space is a cylinder. And on this boundary of the cylinder, we have topological charge A. And on this boundary of the cylinder, we have topological charge A bar, which is its charge conjugate. Now we can apply reflection, where reflection reflects us about this axis of the cylinder. And then that reflection takes A bar from the right side to the left side, giving us RA bar. It takes A to RA over here. So as long as A is equal to RA bar, this is a reflection invariant configuration, and we can define the eigenvalue of reflection. And this is a little bit schematic, but it's good enough. And that eigenvalue is plus or minus 1. So this A to AR is just the eigenvalue under reflection of the state where I have A and A bar on two opposite ends of the cylinder. And this A to AR characterizes symmetry fractionalization for reflection symmetry. Now, just a note for the following slides, in Euclidean field theory, space and time are on equal footing. I'm mainly going to work with the Euclidean field theory and just use R. And in the end, when we want to know results for anti-unitary time reversal symmetry T, so in Lorentzian signature, for example, then we're just going to use the results for R and replace R with CT, where C is charge conjugation. So at various points, I'm going to just freely go back and forth between R and CT. So just be aware that this is what's going on. Okay, now the first thing to note about these symmetry fractionalization quantum numbers, eta AR, is that you need them if you want to determine the Euclidean path integral on non-orientable spacetimes. So remember, if you have a 2 plus 1d TQFT, you can write down the path integral on a closed genus G surface across S1, the circle, and that's given by this famous formula where you sum over all particle types, you have the S matrix, and you raise it to an Euler characteristic. The path integral on a 3-sphere has this formula. So with these eta ARs, now we can also define the path integral on non-orientable spacetimes. For example, we can look at the path integral on the projective plane across S1, where we consider a situation where we have a Wilson loop of A looping around the S1 at a particular point on the projective plane. That's what this ZA is. And the formula for this winds up being a similar formula to what we have here, except now we're studying only over the reflection invariant particles, and this reflection eigenvalue comes in. And it's natural that this reflection eigenvalue would come in because we're looking at the Mobius, the projective plane, and at some point if you want to construct the projective plane, you have to do a reflection twist, which picks up this eigenvalue of eta. Now, from this formula, actually, we can immediately detect anomalies, detect 2-host anomalies. Recall, so this ZA that I just defined, which I'm going to refer to as MA from now on, you can think of this as a dimension of the Hilbert space of the system on where space is RP2 and we have a single puncture labeled by A. Now, if this Hilbert space has dimension greater than 0, then we can pick a state in this Hilbert space, and we can consider doing a Dane twist around alpha. Now the Dane twist around A, well, the Dane twist around the loop alpha, which encircles the particle A. So this Dane twist should pick up the topological twist of the particle that's inside it. On the other hand, this alpha, we can think of it as enclosing the cross-cap instead. And a Dane twist around the cross-cap is actually isotopic to the identity operation. So this means that when we apply this Dane twist, we should actually get the identity. That tells us that theta A needs to be 1 whenever MA is greater than 0. If this is not satisfied, then we have an anomaly. And the anomaly can be resolved by putting the system at the boundary of a 3 plus 1D TQFT. And because the projective plane doesn't bound any 3 manifolds, this is not a problem anymore. Now, we can do a more systematic calculation of these 2-host anomalies. Invertible TQFTs in 3 plus 1D with Z2R symmetry or Z2T symmetry have a Z2 cross Z2 classification. This was discussed by Kapustin. So the idea is that these TQFTs can be classified by the unoriented cobordism group in 3 plus 1 dimensions, which has Z2 cross Z2 classification. Now, there's an interesting point, which is that braided fusion categories B can be used to determine 3 plus 1D TQFTs. This goes back to these papers. So now, furthermore, if B is a modular tensor category, then that means that the associated 3 plus 1D TQFT is invertible. And furthermore, the surface of this 2 plus 1D theory is described by B. So what we can do is we can use these constructions and try to compute the path integral of the 3 plus 1D TQFT on these 2 manifolds, 4-dimensional projective space and 2-dimensional CP2. And these 2 path integrals for the 3 plus 1D theory being plus or minus 1 tell us which of these Z2 cross Z2 states that we're in. However, we can't just blindly use the previous formulations because this is a non-orientable manifold, so we need to extend the previous theories to incorporate the action of reflection symmetry. So I have a few slides about how that works, but let me skip them for now. I'm not sure I'll have enough time. So the final result of the computation is that the path integral in CP2 is given by this formula, which is known to be the exponentiated central charge. This is the famous framing anomaly from TQFTs. But now we have a new formula as well, which is the path integral on RP4, and that's given by this formula. And again, these reflection eigenvalues come in because when we build up RP4 by gluing together manifolds, at some point we have to do a reflection twist. So that's why this eta comes in. And along the course of this, we come up with a pretty non-trivial identity as well, which is everything here. So this is an interesting formula, and I'm going to use it in the next slide. So now these formula, if you think about this for a while, you'll realize that actually now we have some additional consistency conditions on a reflection invariant TQFT. What I told you is that if this H3 obstruction vanishes, then the only other possible anomaly that we could have is a 't Hooft anomaly, where if it exists, the system has to be able to exist at the surface of an invertible 3 plus 1D TQFT. So the H3 obstruction vanishing is equivalent to saying that this 2 plus 1D theory can exist at the surface of a 3 plus 1D invertible TQFT. But if we have a 3 plus 1D invertible TQFT, these two path integrals must be plus or minus 1, right? So we immediately get a highly non-trivial condition, which is that the properties of the theory must be such that when we choose these reflection eigenvalues, this formula needs to be equal to plus or minus 1. If that's not the case, then we have an H3 obstruction. Furthermore, we also just found that this left-hand side also has to be equal to plus or minus 1. It's relatively simple to see why, if this is equal to plus or minus 1, that implies the following interesting condition, which is that these twists are plus or minus 1, and independent of A, for any A where MA is greater than 0. That's a second highly non-trivial condition. A third condition, which doesn't follow from anything I've told you so far, is that this MA must be a non-negative integer for all A. If we have no 't Hooft anomaly and the system is purely 2 plus 1D, you can understand that easily because MA is the dimension of the Hilbert space, so obviously it has to be a non-negative integer. But if the 2 Hooft anomaly does not vanish, it's not obvious that MA would have to be a non-negative integer, but you can still argue for this simply, so maybe it is obvious. So if any of these three conditions is not satisfied, the 2 plus 1D theory cannot exist at the surface of any 3 plus 1D invertible TQFT, and that implies that this H3 obstruction is non-vanishing. So this is pretty interesting because previously, if we wanted to compute the H3 obstruction, we'd have to know all of the F and R symbols, which is extremely difficult to compute. And from there, there's a complicated algorithm for computing the obstruction. Now we can diagnose the existence of these time reversal or reflection obstructions just by looking at the modular data of the theory. We have to be able to find a choice of etas which satisfies all three of these conditions. Now these three conditions are sufficient conditions for the absence, they're sufficient, if these are violated, that's a sufficient condition for the presence of this obstruction. But I don't know that if you satisfy all these, you're guaranteed to not have an obstruction. So I don't know the answer to that question. Okay, so now there's an interesting example that comes up. Let's look at SP4 level 2 Chern-Simons theory. So here I'm using the normalization here where the Lie algebra of SP4 is the same as SO5. Okay, so in the paper, sometimes we write this as USP4 level 2. So it was noticed by these authors that there's a huge class of time reversal invariant TQFTs, of which this SP4 level 2 Chern-Simons theory is one of the simplest ones. And it has the following properties. It has 6 particle types. 2 of these, 1 and epsilon, are simple currents, meaning that so epsilon squares with itself to give the identity. And then we have these other particles. And on the face of it, this looks time reversal invariant if I These are the topological twists, and these are the quantum dimensions. Under time reversal, you can see that these two particles need to get interchanged, and these two particles need to get interchanged. That's denoted here. Now, in this theory, all correlation functions are time reversal invariants. However, when you go and try to compute this path angle in RP4 for the bulk 3 plus 1D theory, then what you find is this formula, which cannot be equal to plus or minus 1 for any choice of these etas. Okay, what happened? Well, this is precisely an example where you have this H3 obstruction. So in this particular case, A is Z2. This H3 cohomology group is Z2. And by direct computation, because we happen to have the F and R symbols in this theory, we can compute that the obstruction is non-trivial. And furthermore, these previous conditions that I mentioned to you, these 3 conditions over here, we can see that they actually are viable. Not only is this path angle not equal to plus or minus 1 for any choice of eta, but furthermore, if we want all the MAs to be integers, then that can only happen if this eta is equal to minus 1. But if we set this eta equal to minus 1, we'll find that m sub psi 1, m sub psi 2 are positive, but the twists are equal to I, which is not equal to plus or minus 1. Okay, so these are things that are so in this way, these previous conditions are violated. So let's look at this SP4 level 2 Turing Simons theory more closely to see what exactly is going on. One way of obtaining SP4 level 2 Turing Simons theory is by starting with SU5 level 1 Turing Simons theory. SU5 level 1 Turing Simons theory has 5 particle types. We can label them J, where J runs from 0 to 4. And SU5 level 1 Turing Simons theory possesses an interesting type of time reversal symmetry, which we call Z4 time reversal. If you define time reversal by taking J to 2J, then what you'll find is that T squares to charge conjugation, and then charge conjugation squares to 1. So T to the 4th is 1 in this case. So what we can do is we can consider gauging the unitary Z2 subgroup of Z4T. So we gauge charge conjugation. Now, when we gauge charge conjugation, we can consider adding a digraph-written term for the Z2 gauge field. So the digraph-written term in this case is classified by H3 Z2 U1 coefficient, which is Z2. So either we add a digraph-written term or we don't add it. We have 2 possibilities. If we add a digraph-written term, the result of gauging charge conjugation is exactly SP4 level 2 Turing Simons theory. If we don't add the digraph-written term, the result is a new theory which has no obstruction, which, for lack of any better term, we call it SP4 level 2 check. Okay? So now, from this point of view, we can understand also, furthermore, what's wrong with SP4 level 2. On the one hand, when we think of SP4 level 2 as gauging SP5 level 1, epsilon is the Z2 gauge charge. Phi 1 and phi 2 are what you get when you, so these particles transform non-trivially under charge conjugation, so you have to group them into orbits, and so that's why you have these 2 particles, phi 1 and phi 2, with quantum dimension 2, each of them. And finally, psi plus and psi minus are the twisted sectors that you get from gauging the Z2. Now, epsilon is the gauge charge, the Z2 gauge charge, meaning it's the T squared gauge charge. Therefore, locally, T squares to minus 1 on epsilon. Eta epsilon is minus 1. However, recall when I first introduced these etas, I told you that eta should be equal to the twist whenever the particle arises from fusion of another particle and its time reversed counterpart. So in this case, epsilon comes from fusion of psi plus and psi minus. And so it must be that eta is equal to theta, which is plus 1, so we have conflicting constraints here. On the other hand, when we look at SP4 level 2 check, we don't have this problem anymore because now these twists are 1 and minus 1, so psi plus and psi minus do not transform into each other under time reversal symmetry. So now we can just set eta epsilon to be minus 1 with no further problems. Now the difference between the obstruction-free theory, SP4 level 2 check, and SP4 level 2 was this digraph-written term. So recall that if we have Z2 gauge theory and we add a digraph-written term, what we get is a theory which is known as the doubled semyon theory. It's the same as U1 level 2 cross U1 level minus 2 Chern-Simons theory. This theory contains 4 types of particles. B, which B is the Z2 gauge charge. S is like the magnetic flux, whose twist goes from 1 to I because of the digraph term. And S prime is what you get by fusing the magnetic flux with the Z2 charge to S prime. So now what I've told you so far can be summarized in the following way. SP4 level 2 is the same as SP4 level 2 check, stacked together with a double semyon theory, but where we have the equivalence where we equate the identity particle with the fusion of B and epsilon. But if we're doing this equivalence, when eta epsilon is minus 1, we must have that eta B is minus 1. But having eta B be minus 1 is inconsistent with the requirement that eta B should be equal to the topological twist of B, which is 1, which holds because we have this. So this is the heart of the problem. The heart of the problem is we have a double semyon theory where we're trying to give the boson the wrong t-squared eigenvalue. Okay? That's why this obstruction is arising. Now, this is a general way to obtain a theory with this Z2T H3 obstruction. We start with a theory which has Z4T symmetry. We gauge T squared while adding a digraph term for the T squared gauge field. All examples that we have can be obtained in this way. I'd be very interested to know if there are ways of getting an H3 obstruction that do not come from this. Other examples are SO4 level 4 Chern-Simons theory and many other examples. So now you can ask, if we have this obstruction, well, how do we resolve this obstruction? How should we think about it? Well, we have 4 possibilities, actually, to think about. Well, maybe 3. The 4th one is actually saying this is not a problem. The first one is we can decide that Z2T was the wrong symmetry. The correct symmetry is actually Z4T. And we can show explicitly that this enlarged symmetry group, Z4T, has no H3 obstruction. Another resolution is that we could view the theory as a spin TQFT, where T squares to minus 1 to the fermion number. That's another way of getting rid of the obstruction. I don't really have time to explain why these work. The third thing, which I want to spend a few slides explaining, is that there's a new type of anomaly inflow that we can think about here, which is that we can view this theory not as a true 2 plus 1D theory anymore, but we can imagine that it's realized, or I use the phrase pseudo-realized, at the surface of a 3 plus 1D non-invertible TQFT. So because the 3 plus 1D theory is non-invertible, this is sort of a new type of anomaly inflow. But the reason I call it pseudo-realized, as you'll see, is that we're not really realizing the 2 plus 1D theory at the surface anymore. We're sort of pseudo-realizing it. There's a final way to think about this H3 obstruction, which is that what you say is that the true symmetry of this theory is actually not Z2T. The true symmetry is that this theory has a 2-group symmetry. The 0-form symmetry, which is Z2T, and the 1-form symmetry A are not independent of each other, but rather they're intimately connected to each other. So you have this 2-group symmetry. Now, the reason I find this a little bit strange and maybe not very useful, at least from a condensed matter physics point of view, is that we want these particles to be dynamical particles of the theory, right? And if you make the particles dynamical, then the 1-form symmetry is no longer an exact symmetry. The 1-form symmetry is really only an exact symmetry where you don't allow dynamical matter content. So for that reason, yes, this is correct, but perhaps not particularly useful if you want to think about the particles as being dynamical excitations. So let me see if in the last minute I can just briefly explain this sort of interesting type of anomaly inflow. So the heart of the problem was this non-existence of a double semyon theory with Z2R symmetry where this eta was minus 1. So I'm going to argue that we can actually realize or pseudo-realize this type of theory at the surface of a 3 plus 1D system by considering our 2 plus 1D system and a bulk 3 plus 1D, where on this plane that goes into the bulk is the mirror plane of the reflection symmetry. And on this mirror plane, I'm going to place a Z2 gauge beam. Now, the Z2 reflection symmetry on the mirror plane acts like a Z2 internal symmetry. So when I look at this junction, I can consider 3 types of edge nodes. I have the edge nodes from the double semyon theory. I have the edge nodes from the double semion theory on the other side of the mirror plane, and then I have edge nodes that come from this Z2 gauge theory on the mirror plane. And if I make a situation where the E and M particles at the mirror plane carry half Z2 charge under this reflection symmetry, then I can gap out all of these edge nodes in such a way that the reflection eigenvalue of the Wilson string for B, which goes across this junction, becomes -1. So it seems like I can precisely realize a situation where the eigenvalue A to BR is -1, but I had to have this mirror plane, this Z2 gauge theory extending into the mirror plane. Now, the reason this is pseudo-realized is because at this junction, the bound state of B and the Z2 gauge charge on the mirror plane is condensed. That means that the boson in the double semion theory, once it hits this junction, can leak out into the bulk. So we don't really have a true 2 + 1D theory anymore. The particles on the surface can leak into the bulk. So in this sense, we haven't really realized the 2 + 1D theory at the surface of 3 + 1D, but we've realized aspects of it. So this is why I use the phrase pseudo-realized. Now, we can continue further. We can have a layer construction, and if we stack 2 + 1D theories and condense pairs of Z2 charges from neighboring planes, and furthermore condense bound states of the boson of the Z2 charge at the surface, then we have a situation where we have a 3 + 1D gauge theory, and the boson on the surface can leak into the bulk, and the semions on the surface become tied to the endpoints of the magnetic flux lines in the bulk. Okay. So what this means is that the transitus theory as before level 2 can sort of exist with this global Z2R symmetry as long as it's pseudo-realized at the surface of this 3 + 1D system, which contains a dynamical Z2 gauge theory. Now, the reason I think we're not crazy here is because a similar phenomenon was also found in a different context, where you have a discrete gauge theory with gauge group D16, this is a dihedral group with 16 elements, and a global Z2 symmetry. In this case, the Z2 symmetry was internal unitary symmetry, not space-time reversing, by these authors. And here they could relate the phenomenon to the notion of symmetry fractionalization of strings in the 3 + 1D bulk. However, this interpretation is not available in the case of space-time reflection symmetry. And finally, this whole procedure can be continued an infinite number of times. We can start with SU5 level 1, gauge T squared, get a theory of obstruction, think of it as Z4T symmetry, gauge T squared again, get another theory of H3 obstruction, we can continue on infinitely. So we get infinite sequence of theories with these H3 obstructions. And we also have an infinite class of root theories with Z4T symmetry that we can start with, which give us these H3 obstructions. So we have many examples. Okay, so let me summarize there. Thank you very much.